Welcome back to the Sleepy Mind channel. Tonight, we explore space, following the movement of matter, energy, and time as they interact across vast distances and shape the universe in steady, observable ways. If you find these long, calm science documentaries useful, you can like the video and subscribe for more. If you choose to leave a comment about where you are listening from, it is always interesting to see how far these stories travel. Let us begin. Space surrounds everything that exists, including the matter that forms stars, planets, and living bodies. It is not an empty backdrop, but a physical setting defined by distance, motion, and measurable limits. The observable universe has been expanding for more than 13 billion years, and the light-reaching telescopes today carries information from events that occurred long before Earth formed. When you look into space, you are not seeing objects as they are now, but as they were when their light began traveling toward you. Light moves at a fixed speed, about 300,000 kilometers per second, which means distance is also a measure of time. A star 10 light-years away is seen as it existed 10 years ago. A distant galaxy, seen billions of light-years away, appears as it was billions of years in the past. At the largest scales, matter in the universe is not distributed evenly. Galaxies gather into clusters. Clusters align along vast filaments, and enormous regions exist where very little matter is present at all. This structure has been mapped through observation and measurement, revealing patterns that extend across hundreds of millions of light-years. These patterns reflect the influence of gravity acting over immense spans of time. Space itself has properties that affect how matter moves. Distances expand as the universe grows, carrying galaxies away from one another without requiring them to move through space in the usual sense. This expansion is measured by shifts in the light emitted by distant objects, known as redshift, which shows that the fabric of space is stretching as time progresses. Within this expanding framework, motion follows predictable rules. Objects with mass influence one another through gravity, shaping orbits, collisions, and long-term stability. Stars form where gravity draws gas together. Planets remain bound to stars through balanced motion. Entire galaxies rotate and drift while remaining part of larger structures. Energy moves through space in many forms. Light carries energy across distances that can exceed the age of planetary systems. Particles travel at high speeds, shaped by magnetic fields and stellar activity. Even regions that appear empty contain low-density gas, radiation, and fields that influence how matter behaves. Time in space does not pass uniformly everywhere. Motion and gravity affect how time is experienced and measured. Clocks on fast-moving spacecraft tick differently from those on Earth. Time near massive objects passes more slowly than time far away. These effects are small at human scales, but become significant in extreme environments. As you continue through this exploration, space becomes less abstract and more structured. It reveals itself as a system governed by physical laws that apply everywhere, shaping motion, energy, and change across distances that are difficult to visualize but precisely measured. This is the environment within which all cosmic processes unfold, continuously and without pause. As attention moves deeper into space, its structure becomes clearer through the behavior of gravity. Gravity is not simply a pull between objects, but a consequence of mass shaping the geometry of space and time. Large concentrations of matter alter the paths that objects and light follow, creating curved trajectories that can be measured and predicted. This curvature becomes visible through observation. Light passing near massive objects bends slightly, producing effects known as gravitational lensing. Distant galaxies appear stretched, duplicated, or brightened when their light travels near clusters of other galaxies on its way toward observation points. These distortions provide direct evidence of how mass influences space across enormous distances. Matter in the universe follows this curved structure. Gas and dust move along gravitational gradients, collecting where curvature is greatest. Over time, this process leads to the formation of stars and galaxies in regions where matter becomes dense enough for gravity to dominate other forces. These regions do not form randomly. Their positions reflect subtle variations in density that were present early in cosmic history. At scales larger than individual galaxies, gravity organizes matter into a web-like pattern. Long filaments of galaxies stretch between massive clusters, while large voids contain very little matter at all. These voids can span tens of millions of light years, yet they are still part of the same continuous structure. The contrast between dense filaments and sparse regions is a direct outcome of gravity acting over billions of years. Within galaxies, gravity governs rotation and stability. Stars orbit the center of their galaxy, following paths determined by the total mass present. Measurements of these rotations reveal that visible matter alone cannot account for observed motion. Additional mass is inferred, known as dark matter, which does not emit light but exerts gravitational influence. Its presence is detected through its effects rather than direct observation. Dark matter forms an invisible framework that shapes galaxy formation. Ordinary matter settles into this framework, collecting where dark matter density is highest. Without this structure, galaxies would not have formed in the way they did. This interaction between visible and invisible components is one of the defining features of cosmic organization. Space also responds to energy. Radiation contributes to the overall balance of forces, especially in the early universe when energy density was high. Even now, background radiation fills space uniformly, carrying information about conditions shortly after the universe became transparent to light. This radiation provides a reference point against which motion and expansion are measured. As space expands, gravitationally bound systems remain intact. Galaxies do not stretch apart internally because their own gravity overcomes the expansion at those scales. Instead, expansion becomes noticeable only across vast distances between unbound systems. This distinction explains why local structures remain stable, while the universe as a whole continues to grow. The structure you are moving through is therefore layered. At small scales, gravity binds planets to stars and stars to galaxies. At larger scales, it arranges galaxies into clusters and filaments. At the largest scales, expansion dominates, carrying structures away from one another over time. This organization is continuous and ongoing. Gravity does not complete its work and stop. It shapes motion and structure moment by moment, responding to changes in mass and energy distribution. As you continue through space, these forces remain active everywhere, guiding the arrangement of matter across distances that far exceed any single point of observation. Energy in space moves according to clear physical limits, even when distances are vast. Radiation travels through space as electromagnetic waves, carrying energy from stars, galaxies, and other sources. This radiation does not require a medium. It propagates through space itself, transferring energy across distances that can span billions of light years. Stars are the dominant sources of energy in much of the universe. Within their cores, nuclear fusion converts mass into energy according to well-defined relationships. Hydrogen nuclei combine to form helium, releasing energy that moves outward through layers of hot plasma before escaping as light and heat. This outward flow of energy balances the inward pull of gravity, creating a stable structure that can persist for millions or billions of years. The energy released by stars shapes their surroundings. Light heats nearby gas and dust, influencing temperature and motion. Radiation pressure pushes material outward, limiting how quickly matter can fall inward. In regions where many stars form together, their combined energy alters the surrounding environment, dispersing gas and slowing further star formation. Motion in space follows predictable patterns governed by conservation laws. Objects in orbit conserve angular momentum, which determines how fast they rotate and how close they remain to one another. When a cloud of gas contracts under gravity, it begins to spin more rapidly as it shrinks. This increase in rotation shapes the formation of disks around young stars and influences the spacing of planets. At larger scales, entire galaxies rotate. Stars orbit the galactic center along paths determined by the total mass enclosed within their orbit. These rotations remain stable over long periods, even as individual stars move relative to one another. The persistence of these patterns demonstrates how energy and motion distribute themselves across complex systems without central control. Collisions and interactions also redistribute energy. When galaxies pass near one another, their mutual gravity distorts their shapes and alters stellar orbits. Gas clouds collide and compress, triggering new star formation. Over time, these interactions change the structure of galaxies while conserving overall energy and momentum. Energy is also carried by particles. High-energy cosmic rays travel through space at speeds approaching that of light, originating from supernovae and other energetic events. These particles interact with magnetic fields, changing direction and losing energy gradually as they move. Their presence reveals ongoing processes, even in regions far from visible sources. Space contains background energy as well. A faint radiation fills all directions uniformly, representing energy released when the universe was much younger and denser. This radiation sets a baseline temperature for space, just above absolute zero. It provides evidence that energy once existed in a far more concentrated state and has since spread out as space expanded. Motion, energy, and structure are therefore inseparable. Energy drives motion. Motion reshapes structure. Structure guides how energy flows. These relationships apply everywhere, from the scale of atoms to the scale of galaxies. As you continue through space, these interactions repeat continuously, creating stable patterns that endure across timescales far beyond individual events. Nothing in space moves without reason. Each trajectory reflects a balance of forces and constraints. Even apparent randomness follows statistical patterns shaped by physical law. The vastness of space does not imply disorder. It reflects systems operating consistently across distances that challenge intuition, but remain governed by the same principles throughout. Stars form where space becomes locally dense with gas and dust. These regions originate within large molecular clouds, which are cold, diffuse structures composed mainly of hydrogen, along with small amounts of helium and heavier elements. Within these clouds, Slight variations in density allow gravity to begin drawing material inward. As gas collects, temperature and pressure increase. The collapsing region fragments into smaller cores, each following its own path towards star formation. Rotation increases as the cloud contracts, flattening material into a disk around the central core. This disk contains the remaining gas and dust that did not fall directly inward. When the central core becomes dense and hot enough, nuclear fusion begins. Hydrogen nuclei combine to form helium, releasing energy in the form of radiation. This energy moves outward, counteracting gravitational collapse. At this point, a stable star is formed, supported by the balance between inward gravity and outward energy flow. The mass of a star determines its entire life cycle. Low-mass stars burn fuel slowly, maintaining steady output for tens of billions of years. High-mass stars consume fuel rapidly, shining brightly, but living for only a few million years. These differences arise from how mass influences temperature, pressure, and fusion rate within stellar cores. Energy generated at the core takes time to reach the surface. In some stars, energy moves outward through radiation, scattering repeatedly through dense plasma. In others, it is transported by convection, with hot material rising and cooler material sinking. These processes regulate surface temperature and brightness, producing stable emission over long periods. Stars interact with their surroundings continuously. Radiation heats nearby material, while stellar winds carry particles outward at high speed. Over time, these outflows shape the surrounding space, clearing cavities and influencing the formation of nearby stars. In clusters, the combined effect of many stars determines how long star formation can continue. Chemical composition also matters. Early stars form from nearly pure hydrogen and helium. Later generations incorporated heavier elements produced by previous stars. These elements influence how gas cools and fragments, affecting star size and formation efficiency. This gradual enrichment alters star formation across cosmic time. Stars do not remain unchanged. As hydrogen fuel in the core is depleted, fusion shifts to different reactions. The structure of the star adjusts, often expanding or contracting in response. These changes occur slowly, unfolding over millions or billions of years, but they determine how energy output evolves. Most stars spend the majority of their existence in a stable phase where fusion proceeds steadily. This stability allows planetary systems to form and persist. Variations in brightness are usually small, reflecting surface activity rather than fundamental changes in energy production. As you move through space, stars appear as fixed points of light, but each represents a complex balance of forces and processes. Their steady glow is the visible outcome of gravity, nuclear physics, and time working together. These processes repeat across the universe, producing light and heat wherever conditions allow matter to concentrate and ignite. Around many stars, the material left over from formation continues to move in organized patterns. This material forms a flattened disk composed of gas, dust, and ice particles, rotating around the young star. Within this disk, small particles collide and stick together, gradually building larger structures over time. These collisions are not random. Differences in mass and velocity cause material to concentrate along preferred paths. Microscopic grains grow into larger aggregates, then into kilometer-sized bodies known as planetesimals. Gravity becomes increasingly important as size increases, allowing these bodies to attract additional material and grow further. Closer to the star, temperatures are high. Only materials with high melting points can remain solid. This region produces rocky planets, composed primarily of silicates and metals. Farther out, where temperatures are lower, volatile compounds such as water, methane, and ammonia can condense. This allows the formation of larger bodies with thick atmospheres and icy cores. As planets grow, their gravity influences nearby material. Gaps form in the disk as planets clear their orbits, accreting matter or scattering it outward. These interactions determine orbital spacing and stability. Systems that form slowly tend to settle into long-lasting configurations, with planets following predictable paths around their star. Gas giants form when a solid core becomes massive enough to attract large amounts of surrounding gas before the disk disperses. This process must occur within a limited time window because radiation and stellar winds gradually remove gas from the disk. If the timing is right, massive atmospheres accumulate. If not, smaller rocky or icy worlds remain. Orbital motion follows precise relationships. Planets closer to the star move faster, completing orbits in shorter periods. More distant planets move more slowly. These patterns arise from the balance between gravitational attraction and forward motion, producing stable trajectories that can persist for billions of years. Interactions between planets also shape system architecture. Gravitational resonances occur when orbital periods form simple ratios. These resonances can stabilize or destabilize orbits depending on configuration. In some systems, planets migrate inward or outward during early stages, altering final positions before settling. Planetary systems are diverse. Observations reveal worlds larger than Jupiter orbiting close to their stars, as well as compact systems with multiple small planets packed into tight orbits. This diversity reflects differences in disk mass, composition, and evolutionary history rather than separate physical laws. Over long periods, planetary surfaces evolve. Impacts, volcanic activity, and atmospheric processes reshape landscapes. Some planets retain thick atmospheres. Others lose them to stellar radiation. These outcomes depend on mass, distance from the star, and magnetic field strength. Planets remain bound to their stars as long as gravitational balance persists. Even as stars age and change, planetary orbits often remain stable. This stability allows systems to endure across timescales far exceeding the duration of individual events. As you continue through space, planetary systems appear as quiet arrangements of motion. Beneath that calm, they represent the outcome of countless interactions governed by gravity, energy, and time. Wherever disks form around stars, similar processes unfold, producing worlds that move steadily through space in long-lasting patterns. Time in space is inseparable from distance and motion. Because light travels at a fixed speed, observing distant objects is equivalent to looking back into earlier stages of the universe. This relationship between distance and time allows space to act as a record of its own history, preserved in the light that continues to travel outward. When telescopes observe nearby stars, the light detected may have left those stars only a few years earlier. Light from more distant galaxies may have begun its journey billions of years ago, when the universe was much younger. As distance increases, observations reveal progressively earlier conditions, allowing reconstruction of cosmic change over time. Stars evolve on timescales that depend on mass. Small stars change slowly, remaining stable for periods far longer than the current age of the universe. Large stars evolve quickly, exhausting fuel in a few million years before undergoing dramatic transitions. These lifetimes determine how energy and elements are distributed across space. Galaxies evolve more slowly. A single rotation of a spiral galaxy can take hundreds of millions of years. Changes in structure occur through gradual processes such as star formation, gas inflow, and stellar death, as well as through rare but influential interactions with other galaxies. Over billions of years, these processes reshape galactic form while preserving overall organization. Time is also affected by motion and gravity. Objects moving at high speed experience time slightly more slowly than those at rest relative to an observer. Strong gravitational fields slow time further. These effects have been measured using precise clocks and must be accounted for in satellite systems operating around Earth. At cosmic scales, they become significant near massive objects such as neutron stars and black holes. The passage of time is not uniform across space. Regions with intense gravity or high velocity experience different rates of change compared to quieter regions. This variation does not disrupt causality, but it demonstrates that time is a dynamic aspect of the universe, rather than an independent background. Large-scale changes in the universe unfold gradually. Expansion stretches distances, cooling matter and radiation over time. Early periods were hotter and denser, while later periods allow complex structures to persist. This steady progression connects present observations with earlier conditions without abrupt transitions. The oldest light observable today originates from a time when the universe became transparent to radiation. Before that point, light could not travel freely. After it, radiation began moving outward uninterrupted. That radiation still fills space, carrying information about temperature and density at that early stage. Time, therefore, links every structure encountered in space. Stars, planets, and galaxies exist within overlapping timelines shaped by formation, evolution, and interaction. Nothing appears suddenly without context. Each object reflects processes that began earlier and continue beyond the present moment. As you move through space, time becomes less like a sequence of events and more like a dimension through which change flows. It governs how energy dissipates, how structures form, and how motion unfolds. Space and time operate together, shaping the universe continuously, without pause or reversal. Change in space often arrives through events that redistribute matter and energy rather than erase them. Among the most influential of these events are the deaths of stars. When a star exhausts the fuel that supports it against gravity, its internal balance shifts, leading to outcomes that depend strongly on mass. Low and medium mass stars expand gradually as their core fuel changes. Outer layers drift outward and are shed into surrounding space, forming extended clouds of gas enriched with elements created during fusion. The remaining core contracts into a dense object known as a white dwarf, which no longer produces energy through fusion, but radiates stored heat slowly over billions of years. High-mass stars follow a different path. When fusion in the core can no longer generate energy, collapse occurs rapidly. The core compresses within seconds, while outer layers rebound outward in a supernova explosion. These explosions release enormous amounts of energy, briefly outshining entire galaxies, and propel material outward at high speeds. Supernovae are primary sources of many elements heavier than iron. The intense conditions during collapse and explosion allow nuclear reactions that cannot occur during normal stellar fusion. These elements are scattered into surrounding space, becoming part of future generations of stars, planets, and living systems. Shock waves from stellar explosions travel through space, compressing nearby gas clouds. This compression can trigger new star formation, linking stellar death directly to birth. The timing and location of these events influence how galaxies evolve over time, creating cycles of formation and destruction that are spatially distributed. Some stellar remnants become neutron stars. These objects contain mass comparable to the Sun, compressed into a sphere only a few tens of kilometers across. Their density is extreme, and their gravitational fields are strong. Many neutron stars rotate rapidly and emit focused beams of radiation that sweep through space, detectable as regular pulses. In the most extreme cases, collapse continues beyond the neutron star stage. Matter compresses until it forms a black hole, a region where gravity becomes so strong that escape is no longer possible. Black holes do not remove material from the universe. They alter how matter and energy are distributed and how nearby space behaves. These events are rare on human timescales, but common over cosmic history. Every galaxy contains the remnants of countless stellar deaths, embedded within gas and dust that continue to participate in new cycles of formation. The distribution of heavy elements throughout space reflects this long history of transformation. Change in space therefore proceeds through redistribution rather than disappearance. Matter shifts form, energy changes state, and structure adjusts accordingly. Even the most violent events contribute to long-term organization by seeding new processes rather than ending them. As you continue through space, the remnants of past change surround you invisibly. The atoms that form planets, atmospheres, and living organisms originate from earlier generations of stars. Space carries this history forward, embedding change into structure and allowing complexity to emerge gradually over immense spans of time. At scales larger than individual stars, these processes combine to shape entire galaxies. Galaxies are collections of billions of stars, bound together by gravity and embedded within extended halos of dark matter. Their overall form reflects how matter settled and moved over long periods of time. Spiral galaxies contain flattened disks where stars orbit in organized patterns around a central region. Spiral arms are not fixed structures, but areas of higher density that move through the disk, compressing gas and triggering star formation as material passes through. This ongoing process maintains the visible pattern without requiring the same stars to remain in the same place. Elliptical galaxies differ in structure. They lack a defined disk and instead contain stars moving along many intersecting paths. These galaxies often form through mergers, where multiple systems combine and redistribute their stars and gas. Star formation in ellipticals tends to slow over time as available gas is consumed or expelled. Irregular galaxies show less organized structure. Their shapes are influenced by interactions, uneven gas distribution, or ongoing star formation. Despite their appearance, their motion still follows gravitational rules, and their evolution reflects the same physical processes seen elsewhere. Galaxies do not exist in isolation. They interact through gravity, sometimes passing close enough to distort one another. Tidal forces stretch stars and gas into long streams, altering orbits and triggering bursts of star formation. Over billions of years, repeated interactions lead to mergers that reshape galactic structure. These mergers redistribute energy and angular momentum. stars settle into new configurations, gas clouds collide and compress, and central regions may become more active. Despite the scale of these events, individual stars rarely collide directly due to the vast distances between them. Dark matter plays a central role in these processes. Although invisible, it contributes most of the mass in galaxies and clusters. Its gravitational influence determines how galaxies move, rotate, and merge. Observations of galaxy motion within clusters show patterns that cannot be explained by visible matter alone, reinforcing the presence of this unseen component. Clusters of galaxies represent the largest gravitationally bound structures in the universe. They contain hundreds or thousands of galaxies moving within a shared gravitational field. Hot gas fills the space between galaxies and clusters, emitting radiation that reveals temperature and density. This gas accounts for a significant portion of ordinary matter in these environments. Beyond clusters, galaxies align along vast filaments separated by large voids. This arrangement reflects the initial conditions of the universe combined with gravitational growth over time. Matter flowed gradually into denser regions, leaving behind expansive areas with very low density. As you move through space at this scale, galaxies appear as steady systems of motion rather than isolated islands. Their shapes, interactions, and distributions record the history of matter responding to gravity across billions of years. These patterns continue to evolve slowly, maintaining structure while accommodating constant change. At the centers of many galaxies lie regions where gravity becomes especially intense. These regions are associated with black holes, whose mass exceeds that of millions or billions of stars combined. Their presence is inferred through the motion of surrounding matter and the energy released as material falls inward. Black holes form when massive stars collapse, or when smaller black holes merge over time. In galactic centers, repeated mergers and sustained inflow of gas allow these objects to grow to enormous size. Despite their name, black holes do not actively draw in surrounding matter. Material must lose energy and angular momentum to fall inward, usually through interactions within dense environments. As gas approaches a black hole, it forms a rotating disk. Friction and compression within this disk heat the gas to extremely high temperatures, causing it to emit large amounts of radiation. This emission can be observed across vast distances, revealing the presence of black holes, even when they cannot be seen directly. Some black holes produce narrow jets of particles that extend far beyond the host galaxy. These jets move at speeds close to that of light and interact with surrounding gas, redistributing energy over large regions. Their orientation and strength depend on rotation, magnetic fields, and the rate at which material is supplied. The influence of a black hole is strongest near its center, but its effects can extend outward through energy output. In some galaxies, this activity regulates star formation by heating or dispersing gas. This feedback limits how quickly galaxies can grow, linking the behavior of central black holes to the evolution of entire systems. The boundary of a black hole is defined by the event horizon, a surface beyond which escape is no longer possible. This boundary is not a physical surface, but a limit set by gravity. Objects crossing it do not encounter a sudden barrier. Instead, they pass a point from which outward paths no longer exist. Time behaves differently near black holes. Strong gravity slows the passage of time relative to distant observers. These effects are predicted by theory and supported by observation. though direct measurement near an event horizon remains beyond current capability. Black holes do not represent breaks in physical law. They are regions where known laws operate under extreme conditions. Their study tests understanding of gravity, motion, and time, providing insight into how space behaves when curvature becomes intense. As you continue through space, black holes become part of a larger pattern rather than isolated extremes. They participate in cycles of growth and interaction, shaping their surroundings while remaining governed by the same principles that apply elsewhere. Their presence reinforces the idea that space is structured and active, even where direct observation is limited. Beyond stars, planets, and galaxies lies the space between them. This space contains low-density gas, dust, radiation, and magnetic fields that influence how matter moves and evolves. Although sparse, this medium plays a significant role in connecting structures across large distances. Gas in interstellar and intergalactic space varies in temperature and density. Some regions are cold and diffuse, while others are heated by radiation or shock waves. Dust grains absorb and scatter light, altering how objects are observed and how energy is distributed. Magnetic fields thread through space, guiding charged particles and influencing gas motion. These fields arise from the movement of charged matter and persist across large scales. Their effects are subtle but measurable, shaping cosmic rays and regulating star formation in some environments. Radiation permeates space in many forms. Starlight, background radiation, and high-energy emissions interact with matter continuously. These interactions transfer energy, change ionization states, and influence chemical reactions even in very low-density regions. Space therefore remains active even where matter is scarce. Processes continue at reduced intensity, but over enormous volumes. This activity links distant regions, allowing energy and material to move gradually across the universe. As the focus shifts toward the present state of the universe, measurement becomes central. Observations of radiation, motion, and structure provide constraints on how fast the universe expands and how matter is distributed. These measurements refine understanding without altering the underlying processes. The universe today reflects a balance between expansion and structure. Galaxies continue to move apart on the larger scales, while local systems remain bound. Energy continues to spread, and matter continues to organize under gravity. As you move toward the edge of this exploration, space reveals itself as neither static nor chaotic. It operates through continuous interaction, governed by physical limits that apply everywhere. Motion, energy, and structure persist without interruption, shaping the universe steadily across time. Observation is how humans first began to understand space beyond immediate surroundings. Long before spacecraft or detectors existed, patterns in light and motion were recorded carefully. The positions of stars were tracked across seasons. The movement of planets was distinguished from the fixed background. These observations revealed regularity rather than randomness, showing that space followed repeatable rules. Telescopes extended this ability by collecting more light than the human eye. Early instruments revealed that faint points of light were not uniform. Some resolved into clusters of stars. Others showed extended shapes that later became recognized as galaxies. Each improvement in resolution expanded the scale at which structure could be measured. Modern telescopes operate across many wavelengths. Visible light reveals stars and galaxies. Infrared light penetrates dust, showing regions of star formation otherwise hidden. Radio waves map cold gas and large-scale structure. High-energy radiation reveals energetic processes near compact objects. Each wavelength contributes different information, allowing space to be studied as a multi-layered system. Measurements of motion provide further insight. By analyzing how light shifts in wavelength, velocities can be determined. These shifts reveal rotation rates of galaxies, expansion of space, and motion within star-forming regions. From these measurements, mass distributions and energy flows can be inferred even when matter itself cannot be seen directly. Spacecraft extend observation beyond Earth. Probes travel through planetary systems, sampling magnetic fields, particles, and radiation directly. Instruments aboard these spacecraft operate continuously, transmitting data that reveals how space behaves locally and how conditions change over time. These measurements confirm that space is dynamic even far from visible objects. Human presence in space remains limited. Life support, radiation exposure, and distance impose strict constraints. Most exploration relies on automated systems designed to function for years without direct intervention. These systems operate according to predictable physical conditions, demonstrating how engineering adapts to the realities of space rather than altering them. As exploration continues, boundaries become clearer. There are limits to resolution, distance, and energy that observation can reach. Some regions are too distant for detailed study. Some processes occur at scales or energies beyond current capability. These limits shape understanding, not by ending inquiry, but by defining where uncertainty remains. The universe today reflects conditions shaped by its long history. Expansion continues, slowly increasing the distance between large-scale structures. Star formation proceeds at varying rates depending on environment. Some regions remain active, while others become quieter as gas is depleted or heated beyond usefulness. Measurements of background radiation show that space retains a faint thermal signature from earlier conditions. This radiation cools as expansion continues, providing a consistent reference against which change can be measured. Its uniformity supports the idea that large-scale conditions were once similar everywhere. Open questions remain. The nature of dark matter and dark energy is still not fully understood. Their effects are measured precisely, but their underlying properties remain uncertain. These unknowns influence expansion, structure formation, and long-term evolution, shaping space in ways that are observed but not yet explained. Despite these uncertainties, space remains governed by consistency. Observations across different regions and times align with the same physical principles. Motion follows predictable paths. Energy is conserved. Structure emerges where conditions allow. These regularities persist even where understanding is incomplete. As this exploration continues, space becomes less distant conceptually. It reveals itself as a continuous system extending beyond immediate perception. Processes observed locally connect to those operating across galaxies and clusters. The same principles apply at every scale, linking observation, measurement, and structure into a coherent whole. The remaining journey moves gradually outward again, away from instruments and measurement, returning focus to the system itself. Space continues to expand, interact, and evolve whether observed or not. Understanding deepens through accumulation rather than conclusion, and the universe remains in motion long after observation ends. As attention shifts back from observation to the system itself, space appears less as a subject of study and more as an environment operating continuously. The processes measured by instruments do not depend on detection. Motion, interaction, and change proceed regardless of whether they are recorded. Expansion remains one of the defining features of the universe at the largest scales. Distances between unbound galaxies increase over time, driven by the stretching of space itself. This expansion is uniform on average, though local variations occur due to gravity. The rate of expansion is measured precisely, yet its underlying cause remains an open area of investigation. Within this expanding framework, structure persists where gravity dominates. Galaxy groups and clusters remain bound, resisting expansion locally. These regions continue to evolve internally, with galaxies orbiting common centers of mass and interacting over long periods. Expansion and binding operate simultaneously at different scales without contradiction. Energy continues to spread through space. Radiation emitted by stars and galaxies moves outward, losing energy gradually as wavelengths stretch with expansion. This redshifting reduces energy density over time, contributing to the long-term cooling of the universe. Matter responds by slowing its activity, forming fewer new structures as available energy decreases. Star formation rates change as a result. In earlier periods, gas was more abundant and denser, supporting frequent star formation. Over time, gas is converted into stars or heated and dispersed. In many regions, this leads to quieter conditions where existing stars dominate and new formation becomes rare. Galaxies reflect this shift. Some retain cold gas and continue forming stars steadily. Others exhaust their supplies and enter long, stable phases dominated by older stellar populations. These differences arise from environment, interaction history, and mass rather than chance. The space between galaxies grows increasingly sparse. Gas density decreases and interactions become less frequent. Yet even in these low-density regions, particles continue to move, fields persist, and radiation passes through. Space never becomes entirely inactive. It transitions gradually toward lower energy states while maintaining structure. Time continues to shape outcomes. Processes that seem slow at human scales accumulate significant change over billions of years. Minor differences in density or motion amplify gradually, producing large-scale patterns. Stability emerges not from stillness, but from balance across time. As the universe evolves, no single moment defines completion. There is no final arrangement toward which space moves. Instead, conditions change continuously, governed by physical limits and initial circumstances. Expansion, cooling, and structure formation proceed together without endpoint. At smaller scales, familiar systems persist. Planetary systems remain bound to stars. Stars orbit within galaxies. Galaxies move within clusters. Each level maintains internal order while participating in larger trends. This layered organization allows continuity even as conditions shift. Space therefore remains coherent across scales. Laws that govern motion and energy apply universally, linking distant regions through consistent behavior. Differences arise from scale and circumstance rather than separate rules. As this journey approaches its later stages, emphasis shifts away from individual structures and toward continuity. Space is not defined by isolated events, but by the persistence of processes. Expansion, interaction, and transformation proceed steadily, shaping the universe across spans of time that extend far beyond observation. The system does not pause or reset. It adjusts continuously, carrying forward the outcomes of earlier states into new configurations. Space remains active, structured, and governed, operating within limits that allow change without collapse. The exploration continues not by reaching an ending, but by recognizing that motion and interaction remain ongoing. Space exists as an environment where processes unfold steadily, connecting past, present, and future through consistent physical behavior. As the scale widens further, the universe begins to appear less crowded and more uniform. On the largest scales observable, matter averages out into broad patterns rather than distinct objects. Galaxies and clusters become points within an overall distribution, and differences in density smooth gradually with distance. This large-scale uniformity is one of the most consistent features of space. Measurements show that when viewed across hundreds of millions of light-years, the universe appears similar in all directions. This does not mean matter is evenly spread everywhere, but that no region is fundamentally different from another at sufficient scale. This principle underlies much of modern cosmology. Uniformity emerges despite local complexity. Dense regions form galaxies and clusters, while vast voids contain very little matter. These contrasts persist, yet they balance when averaged across great distances. Gravity amplifies small differences early on, but expansion limits how much clustering can occur later. Radiation provides another indication of large-scale order. A faint background fills space almost uniformly, carrying information from a time when the universe was far denser and hotter. This radiation has cooled as space expanded, yet its consistency across the sky reveals how evenly conditions were distributed at that earlier stage. As expansion continues, the influence of this radiation diminishes, while matter becomes more isolated within bound structures. Over long periods, galaxies that are not gravitationally bound drift beyond one another's reach. Their light continues to travel outward, but interaction becomes increasingly unlikely. This gradual separation alters how space is experienced across time. Earlier epochs were characterized by frequent interaction and rapid change. Later epochs emphasize persistence and isolation. Neither state is static. They represent different balances between expansion and structure. Energy density decreases as space grows. Matter becomes less concentrated. Processes slow, but they do not cease. Even in regions where star formation has largely ended, existing stars continue to emit light and heat. Gravitational motion continues. Radiation continues to move outward. Time extends these trends without interruption. Given enough duration, differences in energy availability shape the kinds of processes that remain possible. Complex interactions become rarer. Stable configurations dominate. The universe transitions gradually rather than abruptly. Space, therefore, has a direction of change, but not a destination. Expansion does not aim toward a final arrangement. It reflects the continuation of initial conditions under consistent physical laws. Outcomes follow naturally from constraints rather than intention. Within this broad context, individual systems retain significance locally. Planets continue to orbit stars. Stars continue to age and change. Galaxies continue to interact where proximity allows. These processes persist within the larger trend toward lower density and slower change. Understanding space at this scale does not require holding every structure in mind at once. It emerges through recognizing patterns that repeat across size and time. Uniformity and variation coexist, each dominating at different scales. As this exploration moves toward its later phases, emphasis rests on continuity rather than accumulation. Space does not resolve into a conclusion. It remains an environment in which physical relationships continue to unfold, shaped by expansion, gravity, and time acting together. The system remains open-ended. Processes begun billions of years ago continue to operate now, and will continue far into the future, governed by the same principles that shaped the earlier structures and still guide motion across the universe. As attention settles into this wider perspective, the universe appears less as a collection of events and more as a continuous process unfolding across time. Expansion, motion, and interaction do not compete with one another. They coexist, each dominant at different scales, shaping outcomes gradually rather than abruptly. Energy continues to move outward, dispersing across increasing volume. Light emitted long ago still travels through space, carrying information forward even as its energy decreases. This slow redshifting reflects the stretching of space itself, altering how energy is distributed without destroying it. Matter responds by organizing where conditions allow. Gravity gathers material into bound systems that persist despite expansion. These systems remain stable internally, even as the distance between them increases. This separation does not imply isolation in principle, but a change in how interaction occurs across time. Chemical complexity follows these patterns. Elements formed in stars become incorporated into later structures, while lighter elements remain dominant overall. The distribution of elements reflects both early conditions and the cumulative effect of stellar processes. Space carries this record forward through the composition of gas, dust, and solid bodies. Radiation fields weaken, but remain present. Magnetic fields persist across vast regions, guiding charged particles and influencing motion subtly. These fields arise from earlier activity and continue to exist even as environments quieten. Space retains traces of its past through these persistent structures. Nothing in the universe reaches a state of complete rest. Motion continues at every scale, though its expression changes. Orbits persist, particles drift, expansion proceeds, change slows in some regions while remaining active in others. Balance shifts rather than resolves. From this perspective, space is neither beginning nor ending. It is a system in transition, shaped by initial conditions and constrained by physical law. What appears distant or abstract becomes a matter of scale rather than separation. As this exploration moves closer to its later stages, emphasis rests on persistence. Processes that began early continue now, adjusted by time and circumstance. Space carries its own history forward without interruption, maintaining coherence through consistency rather than control. The universe remains active not because it is driven toward a goal, but because motion and interaction are inherent to its structure. Expansion does not erase organization. It redefines how organization appears across time. The journey through space, therefore, does not conclude with an endpoint. It reaches a point of equilibrium in understanding, where patterns become familiar and motion becomes expected. What remains is continuity rather than surprise. Space continues to expand. Matter continues to interact. Energy continues to move. These processes remain in balance, unfolding steadily across time that extends far beyond observation. This is the environment within which everything exists, operating quietly and persistently, governed by limits that allow change without collapse and continuity without stillness. As this exploration continues, space can be understood less through individual components and more through the relationships that connect them. What matters most is not any single star, galaxy, or structure, but how energy, matter, and time interact repeatedly under consistent conditions. Interactions in space often occur over long intervals. A gas cloud may drift for millions of years before encountering a region dense enough to trigger collapse. Two galaxies may approach one another slowly, taking hundreds of millions of years before interaction alters their structure. These extended timescales allow processes to unfold gradually, reducing instability and allowing systems to adapt. Small differences accumulate significance through repetition. Slight variations in density influence where matter collects. Minor differences in motion alter long-term trajectories. Over time, these effects shape large-scale outcomes without requiring sudden change. Space evolves through accumulation rather than interruption. Feedback plays a central role. Energy released by stars influences surrounding gas, which in turn affects future star formation. Activity in galactic centers regulates growth at larger scales. These feedback mechanisms limit extremes, preventing unchecked collapse or runaway expansion within bound systems. Space also exhibits thresholds. Certain processes occur only when conditions cross specific limits. Fusion requires sufficient temperature and pressure. Star formation requires cooling below particular thresholds. Planet formation depends on the availability of solid material. These limits define when and where complexity can arise. Once conditions change beyond these thresholds, processes slow or cease locally. Regions lacking sufficient density remain diffuse. Systems that exhaust fuel enter stable phases. These transitions do not reverse earlier outcomes, but they do shape what remains possible. Observation reveals that no region of space exists entirely alone. Radiation from distant sources passes through all areas. Gravitational influence extends outward indefinitely, though it weakens with distance. Fields and particles move across large volumes, linking regions that appear separate. This connectivity does not imply uniformity. Conditions vary widely. Some regions remain active and luminous, others become quieter and darker. Both states emerge from the same governing principles applied under different circumstances. Space therefore supports diversity within constraint. It allows a wide range of structures while limiting how extreme those structures can become. This balance between freedom and restriction underlies the persistence observed across cosmic history. As the focus moves toward the later phases of this journey, attention rests on continuity rather than novelty. The processes encountered earlier continue to operate, reshaped by scale and time, but not replaced. Motion remains present. Interaction remains possible. Change continues without urgency. The system does not build toward a final configuration. It adjusts continuously, shaped by expansion, gravity, and energy flow. Understanding emerges not from reaching an endpoint, but from recognizing how these influences remain active everywhere. Space remains an environment defined by relationship. Matter shapes space. Space guides motion. Time integrates change. Together, they form a system that operates steadily, extending far beyond any single observation or moment. As this understanding settles, the vastness of space becomes less overwhelming and more structured. What once seemed empty reveals itself as active. What once seemed distant becomes governed by familiar principles. The universe continues to unfold, not toward conclusion, but through sustained, ordered change. As the final phase of this exploration approaches, attention shifts gently away from structure and toward persistence. The universe does not signal an ending point. It maintains continuity through processes that repeat and adjust rather than conclude. Expansion continues without interruption. Distances increase, energy density decreases, and large-scale interaction becomes less frequent. Yet this does not remove organization. It changes the scale at which organization is most visible. Bound systems remain active long after their surroundings become sparse. Within galaxies, stars continue to age and emit light. Some will exhaust their fuel slowly, others more quickly, but all follow predictable paths, shaped by mass and environment. Planetary systems remain stable where conditions allow. Motion persists even as creation slows. Radiation continues to travel outward, carrying information forward through time. Light emitted now will pass through regions that may one day contain little matter at all. Even then, that radiation will still exist, stretched but not erased, maintaining a record of earlier states. Gravitational influence never fully disappears. It weakens with distance, yet it extends indefinitely. Even isolated systems remain connected through the geometry of space itself. This connection is subtle, but it is never absent. The future of space is shaped by the same principles that governed its past. Energy spreads, matter organizes where possible. Change slows, but does not stop. There is no sudden transition between activity and stillness, only gradual adjustment toward lower intensity states. From this perspective, space is not defined by dramatic events, but by endurance. Its most important features are not explosions or collisions, but the consistency with which physical law applies across time and distance. Understanding this continuity allows the vast scale of space to feel less remote. It becomes a system that behaves reliably, even when outcomes are uncertain. Predictability exists at the level of process, if not at the level of individual events. As this journey draws toward a natural close, nothing within the universe itself changes course. Motion continues, expansion proceeds, interaction remains possible wherever conditions permit. What concludes here is only the act of observing. The system remains active beyond description, operating according to limits that allow persistence without resolution. Space continues as it always has, not as a destination reached, but as an environment sustained by balance, governed by consistent principles, and extended across time without pause. Between stars and galaxies, space contains matter that is sparse but influential. This material is known as the interstellar medium within galaxies and the intergalactic medium between them. Although its density is extremely low compared to planetary or stellar environments, it occupies vast volumes and plays a central role in how space evolves. The interstellar medium consists primarily of hydrogen and helium, with small amounts of heavier elements. It exists in several phases distinguished by temperature and density. Cold regions contain dense molecular gas, where temperatures can fall to only a few degrees above absolute zero. Warmer regions contain diffuse atomic gas, while the hottest components are thin plasmas, heated by radiation and shock waves from stellar activity. These phases are not static. Energy input from stars continuously shifts material between them. Radiation heats gas and causes it to expand. Cooling allows gas to condense. Shock waves from supernovae compress and stir surrounding material, creating turbulence that redistributes energy and matter. This cycling regulates when and where new stars can form. Dust is a small but significant component of this medium. Dust grains are microscopic solid particles composed of carbon, silicates, and other compounds. They absorb and scatter light, affecting how distant objects appear. Dust also provides surfaces on which molecules can form, including molecular hydrogen, which is essential for star formation. Without dust, many chemical processes would proceed far more slowly. Magnetic fields thread through the interstellar medium and influence how charged particles move. These fields arise from the motion of ionized gas and persist across large regions. They guide cosmic rays, affect gas compression, and help regulate the collapse of clouds into stars by providing additional resistance to gravity. On larger scales, the intergalactic medium contains even lower densities of gas. Most of the ordinary matter in the universe resides not in stars or galaxies, but in this diffuse state. It forms filaments connecting galaxies and clusters, tracing the same large-scale structure shaped by gravity. Observations of distant light passing through this medium reveal its composition and temperature through subtle absorption features. Radiation passing through these regions interacts continuously with matter. Ultraviolet light ionizes gas. X-rays heat diffuse plasma. These interactions alter chemical states and influence how matter behaves over long periods. Even in near emptiness, energy exchange continues. The interstellar and intergalactic media act as reservoirs and pathways. They store material expelled by stars and galaxies and later deliver it back into new structures. This slow circulation connects stellar birth, evolution, and death across time and distance. As you continue through space, this diffuse matter surrounds everything. It fills the gaps between visible objects, shaping how light travels, how energy dissipates, and how future structures become possible. Space between stars is not inactive. It is the medium through which change moves gradually, linking isolated systems into a continuous whole. Radiation and fields extend through space alongside matter, shaping conditions even where particles are few. Radiation exists as energy traveling through space in the form of electromagnetic waves, while fields describe regions where forces influence motion without direct contact. Together, they connect distant regions and regulate how matter behaves over time. Electromagnetic radiation spans a wide range of wavelengths. Radio waves travel through space with little interaction, revealing large-scale structure and cold gas. Infrared radiation traces heat and dust. Visible light carries information about stars and galaxies. Higher energy radiation such as ultraviolet, X-rays, and gamma rays originates from energetic environments and compact objects. Each wavelength interacts with matter differently, altering temperature, ionization, and motion. Radiation transfers energy continuously. When light is absorbed by gas or dust, it increases particle motion and raises temperature. When matter emits radiation, it loses energy and cools. This exchange determines whether regions remain diffuse or collapse into denser structures. Cooling through radiation is essential for star formation, allowing gas clouds to shed energy and contract under gravity. Background radiation fills all of space. This faint signal remains from an early stage when matter and radiation were closely coupled. As space expanded, this radiation cooled and spread uniformly. Today, it provides a consistent reference temperature for the universe, just above absolute zero. Its uniformity reflects the large-scale smoothness of early conditions. Fields influence motion without requiring physical contact. Gravitational fields shape trajectories across all scales, from planetary orbits to galaxy clusters. Electromagnetic fields affect charged particles, guiding their paths and altering energy distribution. Magnetic fields, in particular, play a subtle but important role in space. Magnetic fields arise wherever charged particles move. In space, these fields are generated by rotating stars, galactic disks, and turbulent plasma. Once formed, magnetic fields persist and extend across large regions. They influence how gas flows, how shock waves propagate, and how cosmic rays travel through space. Cosmic rays are high-energy particles that move through space at nearly the speed of light. They originate from supernova remnants, stellar winds, and energetic galactic centers. Magnetic fields deflect their paths, causing them to scatter and diffuse rather than travel in straight lines. This scattering distributes energy over wide areas and influences chemical reactions in gas clouds. Fields and radiation together shape the environment between stars and galaxies. They regulate temperature, control particle motion, and influence how matter responds to gravity. These effects accumulate gradually, producing large-scale outcomes from subtle interactions. Nothing in space exists entirely outside the influence of radiation and fields. Even the most diffuse regions are permeated by energy and force. These components provide continuity, linking distant systems through invisible connections that persist regardless of distance. As you continue through space, radiation and fields operate quietly and constantly. They do not announce their presence through dramatic events. Instead, they shape motion and change through steady influence, ensuring that space remains active and connected, even where matter is sparse. Human interaction with space has always depended on indirect contact. Unlike environments on Earth, space cannot be entered or altered easily. Understanding comes from measurement rather than immersion, using instruments that translate distant signals into usable information. Telescopes are extensions of this process. They do not simply magnify distant objects. They collect radiation across different wavelengths and separate it into measurable components. By analyzing brightness, color, and variation over time, properties such as temperature, composition, motion, and distance can be determined with precision. Each type of telescope reveals different aspects of space. Optical instruments show stars and galaxies as patterns of light. Radio telescopes detect cold gas and large-scale structure invisible at shorter wavelengths. Infrared instruments penetrate dust, exposing regions where stars are forming. High-energy detectors capture emissions from compact objects and energetic events. Together, these views build a layered understanding of the same environment. Measurement depends on calibration and reference. Distances are established using predictable relationships, such as how brightness changes with distance or how certain objects behave intrinsically. Motion is inferred through shifts in radiation. Mass is estimated through gravitational influence. These methods rely on consistency rather than direct access. Spacecraft extend observation closer to sources. Probes travel through planetary systems, sampling particles, magnetic fields, and radiation directly. Instruments on board operate continuously, recording changes over time rather than isolated snapshots. This reveals how space behaves dynamically, responding to solar activity, planetary motion, and interaction with radiation. Human presence beyond Earth remains rare and constrained. Distance, radiation exposure, and resource limits restrict how far and how long people can travel. Most exploration relies on automated systems designed to function without intervention for years or decades. These systems do not change the environment they study. They adapt to it. Limits are fundamental to exploration. Some regions are too distant for detailed resolution. Some processes occur at energies or scales beyond current detection capability. Observation always contains uncertainty, shaped by instrument sensitivity, signal interference, and physical limits, such as the speed of light. These limits do not halt understanding. They define boundaries within which reliable conclusions can be drawn. Where data becomes sparse, uncertainty increases gradually rather than abruptly. Space is understood not through complete knowledge, but through consistent patterns observed across many regions and conditions. Despite constraints, measurements align across different methods. Independent observations converge on similar values for expansion rate, structure distribution, and composition. This consistency reinforces confidence in underlying principles, even where details remain unresolved. As observation continues, space becomes more familiar conceptually without becoming smaller. It remains vast and inaccessible, yet governed by relationships that can be measured and tested. Human understanding grows through accumulation rather than conquest, shaped by the ability to interpret signals rather than occupy space directly. This relationship places humans within space rather than outside it. Observation does not separate observer and environment. It links them through physical interaction, allowing distant processes to influence instruments, and through them, understanding. As observation improves, so does awareness of what cannot yet be resolved. Space presents limits that are not temporary gaps in knowledge, but fundamental constraints imposed by physics itself. Distance, energy, and time place boundaries on what can be measured directly and how precisely it can be known. Light speed sets the first of these limits. Signals from distant regions take time to arrive, and some regions lie beyond the distance from which light has had time to reach observation points. These regions may exist, but they cannot influence current measurements. Understanding is therefore limited to the observable portion of the universe, rather than the entirety of what may exist. Resolution imposes another boundary. Even the most powerful instruments can only distinguish features down to a certain scale. Distant objects blur into single points of light. Structures smaller than that scale cannot be separated. As distance increases, fine detail is lost, replaced by average properties such as total brightness or spectral signature. Energy sensitivity also constrains detection. Some processes release very little radiation. Others emit energy at wavelengths difficult to capture. Background noise further limits clarity, especially when signals are faint. Instruments must separate meaningful patterns from random variation, which becomes more challenging as signals weaken. There are limits imposed by interaction itself. Measuring a system can alter it, particularly at small scales. While this effect is negligible for large cosmic structures, it becomes significant when interpreting high-energy particles or extreme environments. Some properties cannot be measured simultaneously with arbitrary precision. These constraints shape how questions are framed. Instead of asking for exact states, observation focuses on distributions, averages, and probabilities. Large-scale behavior becomes clearer than individual detail. Patterns emerge even when components cannot be resolved fully. Uncertainty is therefore not a flaw, but a condition of working within physical law. It narrows gradually, rather than disappearing. Over time, repeated measurements refine estimates, and reveal consistency across independent methods. Confidence grows through convergence rather than completeness. Space accommodates both clarity and uncertainty simultaneously. Some properties are measured precisely, such as the expansion rate or the speed of light. Others remain bounded within ranges that reflect observational limits. This balance allows understanding to advance without requiring total access. As you continue through space conceptually, these limits define the edges of knowledge rather than the edges of existence. What cannot be measured directly still follows the same physical principles as what can be observed. Unknown does not imply unstructured. This perspective shifts emphasis away from final answers and towards stable frameworks. The universe is understood through relationships that persist, even where detail is inaccessible. Gravity behaves consistently. Energy is conserved. Motion follows predictable paths within known constraints. As the journey continues, these limits remain present, guiding interpretation rather than closing it. Space remains open to further refinement, shaped by measurement that advances carefully within the boundaries set by nature itself. Space today reflects conditions shaped by both early structure and long-term expansion. The universe is older, larger, and cooler than it was when the first stars formed. These changes affect how matter behaves and how frequently new structures appear, but they do not interrupt the underlying processes that govern motion and interaction. Expansion remains measurable in the present era. Distant galaxies continue to move away from one another on average, with speed increasing with distance. This relationship has been confirmed through extensive observation and remains consistent across different regions of space. Local variations occur due to gravity, but the overall trend persists uniformly at large scales. This expansion influences energy distribution. As space stretches, radiation loses energy through redshifting. Wavelengths lengthen, and energy density decreases. Over time, this reduces the ability of radiation to influence matter directly, contributing to slower rates of change in many regions. Matter responds by settling into stable configurations where gravity dominates locally. Dark matter continues to shape structure even as expansion progresses. Although it does not emit or absorb light, its gravitational influence remains measurable. It defines the framework within which galaxies and clusters reside. As ordinary matter becomes more diffuse, dark matter maintains the large-scale patterns established earlier, preserving coherence across vast distances. Another component influences expansion at the largest scales. Observations indicate that the rate of expansion is increasing over time. This behavior is attributed to a form of energy associated with space itself, often referred to as dark energy. Its effects are not noticeable within bound systems, but they become significant across intergalactic distances. Dark energy does not cluster or form structures. It acts uniformly, contributing to accelerated expansion without introducing local variation. This influence becomes more prominent as matter density decreases, gradually shaping the future behavior of space at the largest scales. Despite these influences, most of the universe remains governed by familiar dynamics. Stars continue to orbit within galaxies. Galaxies continue to move within clusters. Planetary systems remain bound to their stars. Expansion alters relationships between distant systems, but it does not disrupt internal stability where gravity is dominant. Space today, therefore, represents a balance between persistence and change. Early formed structures remain intact, while large-scale separation increases. Energy spreads, but it does so gradually. Interaction becomes less frequent across long distances, while remaining active locally. These conditions suggest a future where structure becomes increasingly isolated rather than erased. Bound systems persist, carrying forward earlier complexity, even as surrounding space grows quieter. This transition unfolds over timescales far beyond immediate observation, without abrupt shifts. As this exploration continues, emphasis remains on present behavior rather than projection. Space today is active, structured, and measurable. It reflects both its origin and its ongoing evolution, shaped by expansion, gravity, and energy acting together without interruption. As the universe continues to evolve, conditions gradually favor persistence over creation. Energy density decreases, matter becomes more dispersed, and opportunities for new structure arise less often. This does not remove complexity, but it changes where and how complexity appears. In earlier periods, dense gas clouds were common, supporting frequent star formation. Today, much of that gas has already been incorporated into stars or heated beyond the point where it can collapse easily. Star formation still occurs, but it is concentrated in specific environments rather than widespread across space. Galaxies reflect this shift clearly. Some remain active, containing reservoirs of cold gas that continue to form new stars. Others have largely exhausted their supplies and now consist mainly of older stellar populations. These galaxies change slowly, dominated by long-lived stars that evolve over billions of years. The decrease in available energy alters how systems interact. Collisions and mergers become less frequent as expansion increases separation. Where interactions still occur, they follow the same physical rules as before, but their overall contribution to change diminishes with time. Radiation continues to cool as space expands. Background radiation becomes increasingly faint. Local sources dominate energy input within bound systems, while the influence of distant sources weakens. This shift emphasizes local processes over large-scale interaction. Despite these trends, motion does not cease. Orbits remain stable. Gravitational influence persists. Particles continue to move through space, guided by fields and forces. Change slows, but it does not stop. This gradual transition illustrates how space evolves without reaching a final state. There is no moment when activity ends. Instead, processes become less intense and more evenly distributed. The universe adjusts continuously, maintaining coherence across changing conditions. From this perspective, time does not drive space toward an outcome. It allows existing relationships to play out within expanding boundaries. What remains important is not what ends, but what persists. As you continue through this environment, the emphasis shifts naturally toward endurance. Structures that have formed remain, governed by stability rather than rapid transformation. Space continues to function as a setting where motion and interaction occur steadily, even as opportunities for novelty become rarer. This phase of space is not quieter because it is empty, but because it is settled. Energy has spread, matter has organized. Processes continue at a pace shaped by long history rather than immediate change. Understanding this progression reinforces the continuity of space. The same principles that governed early formation now govern long-term persistence. Nothing new is introduced, nothing essential is removed. Space remains active within limits, that allow it to continue indefinitely. Even as conditions favor persistence, space never becomes disconnected. Separation increases at large scales, but relationships remain embedded in structure and law. Systems that no longer interact directly still follow the same physical rules, shaped by the same constraints that govern their formation. Bound structures retain internal coherence. Planetary systems remain organized by gravity. Stars continue to orbit within galaxies. Galaxies remain arranged within clusters where binding forces exceed expansion. These systems do not drift apart internally because their local dynamics dominate over large-scale trends. Connection therefore shifts from interaction to consistency. Objects no longer exchange matter or energy directly across great distances, but they remain linked through shared origin and governing principles. The same constants apply everywhere. The same relationships between mass, energy, and motion persist across all regions. Fields continue to provide subtle linkage. Gravitational influence extends indefinitely, even if its effects weaken with distance. Radiation continues to pass through space, carrying information forward even when no receiver is present. These connections do not require proximity. They exist as part of the structure of space itself. Time integrates these relationships rather than erasing them. Past interactions shape present conditions. Earlier distributions of matter determine where stability remains. The future unfolds from these existing arrangements without requiring new input. At this stage of the journey, emphasis rests on recognizing how little is required to maintain coherence. Space does not need continual renewal to persist. It requires only that underlying laws remain unchanged. With that consistency, structure endures even as activity slows. Variation continues at smaller scales. Local environments remain dynamic. Stars evolve, planets change, fields fluctuate. These changes occur within stable frameworks that limit how far deviation can extend. Balance emerges from constraint rather than control. Space therefore supports both change and sameness simultaneously. Novelty becomes rarer at the larger scales while remaining present locally. This layered behavior allows the universe to evolve without destabilizing its foundations. As you continue through space, this balance becomes the dominant theme. The universe is neither static nor chaotic. It operates through steady adjustment, guided by physical law and shaped by accumulated history. There is no requirement for conclusion. Processes do not wind down towards silence. They continue within expanding boundaries, maintaining coherence through consistency rather than intensity. The system remains open, not because it awaits completion, but because motion and interaction are intrinsic. Space persists as an environment where relationships continue to unfold, governed by the same principles that have applied throughout its existence. As space continues to expand and conditions settle, attention turns to how scale alters perception. At human scale, distances are measured in kilometers and time in years. At cosmic scale, distances span light years and time extends across billions of years. The same physical laws apply, but their effects become apparent only through accumulation. Scale determines which processes are visible. At small scales, motion appears rapid and change feels immediate. At large scales, motion is slow and change is subtle. A galaxy may complete a single rotation over hundreds of millions of years, yet its internal structure remains coherent throughout that time. This stability emerges not from stillness, but from balance across long intervals. Energy flow reflects this scaling. A star emits vast amounts of energy every second, yet the effect on surrounding space unfolds gradually. Radiation spreads outward, interacting weakly with distant matter. Over time, this continuous emission shapes temperature, ionization, and motion across large regions without requiring concentrated bursts. Matter responds similarly. Small forces acting persistently produce large outcomes. Slight gravitational attraction gathers material over millions of years. Minor differences in density influence where structures form. These effects are negligible in isolation, but decisive when repeated across vast spans of space and time. This scaling explains why space appears calm despite ongoing activity. Processes operate steadily rather than dramatically. Change occurs through integration rather than interruption. The universe evolves by allowing effects to compound gradually within consistent limits. At intermediate scales, this balance is especially clear. Star clusters form and disperse. Gas clouds condense and fragment. Planetary systems adjust slowly as stars evolve. These processes bridge the gap between local activity and cosmic trends, linking small-scale dynamics to large-scale structure. Scale also shapes uncertainty. Some processes cannot be resolved because they occur too slowly or across distances too great to observe directly. Instead, they are inferred through long-term patterns and statistical consistency. Space reveals itself through these average behaviors rather than isolated moments. As observation continues, understanding improves not by speeding up perception, but by extending it across time. Repeated measurements accumulate clarity. Long-term monitoring reveals trends invisible in short intervals. Space becomes intelligible through patience rather than immediacy. This relationship between scale and understanding reinforces the continuity of space. Nothing changes abruptly without cause. Large outcomes arise from small influences applied consistently. Stability emerges from constraint rather than control. As you move further through this exploration, scale becomes a guiding principle. It explains why space can remain active without appearing chaotic, and why complexity persists even as energy spreads and interactions become less frequent. The universe continues to operate across all scales simultaneously. Local systems remain dynamic. Large-scale structure adjusts slowly. Both behaviors coexist, linked by physical law and shaped by time. This layered operation allows space to evolve continuously, maintaining coherence across distances that far exceed any single frame of reference. As this journey moves further through space, the emphasis remains on how continuity replaces accumulation. Early periods were defined by frequent formation and interaction. Later periods are defined by maintenance of what already exists. This transition is gradual and governed by the same principles that shaped earlier change. Structures that formed under denser conditions persist because their internal balances remain intact. Stars continue to burn fuel, planets continue to orbit, galaxies continue to rotate. These motions require no external input beyond the energy and momentum already present. Stability emerges because lost processes operate slowly relative to system size. Energy continues to dissipate, but not uniformly. Within bound systems, energy remains concentrated and useful. Outside them, energy spreads and weakens. This separation reinforces the distinction between active regions and quiet regions, without creating discontinuities. Space accommodates both simultaneously. Over long periods, differences between environments become more pronounced. Regions rich in structure remain locally complex. Regions between them grow increasingly sparse. This contrast does not imply loss of organization. It reflects redistribution shaped by expansion and gravity acting together. Time integrates these differences smoothly. Processes do not terminate when conditions change. They adapt. Star formation slows where gas is depleted. Motion persists where energy remains. Radiation continues to travel, regardless of local environment. Space evolves by adjusting rates, rather than switching behaviors. Understanding this progression removes the need for dramatic interpretation. The universe does not approach an ending state in any meaningful sense. It approaches lower energy density while retaining internal coherence. This outcome is a natural consequence of expansion operating under conservation laws. At this stage of exploration, the system is best understood through endurance. What persists does so because it is stable under changing conditions. What fades does so gradually, without abrupt disappearance. Space maintains continuity by allowing processes to slow rather than stop. Local complexity remains possible for long durations. Stars like the Sun will continue to emit light for billions of years. Planetary systems remain ordered far beyond the lifespan of individual observers. These systems operate independently of large-scale change, protected by gravitational binding. As you continue through space conceptually, the emphasis remains on how little is required to sustain structure. No guiding force directs outcomes. Physical law alone shapes evolution through constraint and balance. This view reinforces the character of space as an environment defined by relationship rather than event. Motion, energy, and time remain intertwined, operating steadily across scales that extend beyond immediate perception. The exploration continues without urgency. Space remains active, structured, and governed, allowing processes to persist through time that extends far beyond observation or description. As perspective continues to widen, space becomes easier to understand through what remains consistent rather than what changes. Across every region examined, the same relationships between mass, energy, motion, and time apply. Differences arise from scale and circumstance, not from altered rules. This consistency allows space to function as a single system rather than a collection of isolated regions. Conditions vary, but behavior remains predictable within known limits. Where matter gathers, gravity dominates. Where energy spreads, change slows. Where density is low, interaction becomes rare but never absent. The persistence of physical law across distance is one of the most important features of space. Experiments conducted near Earth produce results that match observations made across galaxies. The same constants govern atomic interactions and cosmic motion. This universality links the smallest structures to the largest without requiring modification. As expansion continues, this consistency becomes more apparent. Structures separate, but they do so in accordance with the same relationships that govern their formation. No new behavior emerges simply because distances increase. Space grows, but it does not change character. Time integrates this behavior smoothly. Earlier states influence later ones through preserved momentum and distribution of matter. Later states reflect accumulated outcomes rather than sudden transitions. Space evolves through continuity rather than replacement. At this stage of the journey, understanding comes from recognizing how little adjustment is required for the universe to persist. Systems do not need external intervention to continue. They require only that conditions remain within tolerances established by physical law. Even as energy density declines, complexity does not vanish. It becomes localized. Regions that formed under favorable conditions continue to operate independently. Stars burn steadily. Planets follow stable paths. Galaxies maintain structure despite increasing separation from one another. Space therefore supports long-term persistence without stagnation. Motion continues. Interaction remains possible. Change unfolds gradually. This balance allows the universe to remain active across timescales that extend far beyond any single epoch. As the exploration moves onward, emphasis remains on coherence rather than accumulation. The universe does not progress toward an endpoint. It maintains continuity through consistent behavior applied across expanding scale. This view reframes vastness as stability rather than emptiness. Space is large because it allows processes to unfold without interference. Distance provides room for motion and adjustment rather than isolation. The system remains open, governed, and continuous. Space persists not because it is static, but because its structure allows change to occur without destabilization. This persistence defines the environment within which all cosmic processes continue to unfold. As the universe continues under these conditions, the role of history becomes increasingly important. Present structure reflects not only current forces, but the accumulated outcome of earlier states. Where matter gathered early, stability persists. Where density remained low, large-scale structure never developed. These initial differences continue to shape behavior long after formation has slowed. Memory in space is carried through distribution rather than record. The placement of galaxies, the composition of gas, and the abundance of elements all reflect earlier processes. Space does not forget. It retains outcomes through configuration rather than through stored information. Each region carries the imprint of past interaction in its present arrangement. This persistence allows prediction without direct observation of origins. By measuring present conditions, earlier stages can be inferred. Expansion rate, composition, and structure reveal the sequence of change that led to current form. Space therefore remains intelligible even where direct access to the past is impossible. As expansion continues, future interaction becomes increasingly limited to bound systems. Galaxies outside these systems drift beyond influence. Light emitted now will not reach some regions in the distant future. This separation is gradual and predictable, governed by expansion rather than disruption. Within bound systems, internal time remains meaningful. Orbits continue. Energy cycles persist. Local processes operate independently of large-scale separation. This distinction between local continuity and global divergence defines the long-term behavior of space. Energy loss through radiation continues, but its effects remain distributed unevenly. Regions with active stars retain usable energy. Regions without them cool and darken. This contrast increases over time, not through sudden change, but through accumulation of small differences applied consistently. Despite these trends, no boundary appears between activity and inactivity. Space transitions smoothly. Regions become quieter without becoming disconnected from physical law. Motion persists even where interaction becomes rare. As this understanding deepens, space appears less like a sequence of events and more like a long adjustment governed by constraint. Expansion, gravity, and energy flow remain active simultaneously, shaping outcomes without requiring intervention. This perspective removes the need for resolution. Space does not aim toward a state of completion. It continues to evolve within expanding limits, maintaining coherence through consistency rather than intensity. As the journey continues, emphasis remains on how structure endures through change. The universe persists, not by resisting expansion, but by allowing local stability within it. This balance defines the long-term character of space as an environment that continues to operate quietly, steadily, and predictably across time that extends far beyond observation. As this exploration continues, space becomes increasingly defined by how processes slow rather than how they stop. Activity does not disappear. It stretches out across longer intervals, shaped by decreasing density and widening distance. Change becomes subtle, but it remains continuous. Within bound systems, internal cycles persist. Stars continue converting mass into energy. Planets continue to follow stable paths. Magnetic fields fluctuate and adjust. These processes do not depend on external input. They draw on conditions established earlier and continue until internal limits are reached. Outside these systems, space grows quieter. Matter becomes more diffuse. Interactions occur less frequently, but they do not vanish. Particles still move. Radiation still travels. Fields still extend across regions that contain little else. Even in extreme sparsity, physical law remains active. This contrast between active interiors and quiet expanses becomes one of the defining features of later cosmic conditions. It is not a division between presence and absence, but between concentration and dispersion. Both states coexist within the same framework. Time integrates these differences gradually. What appears static over short intervals reveals change when viewed across billions of years. Minor adjustments accumulate into significant shifts. Space evolves through this accumulation without requiring dramatic transitions. Understanding space at this stage requires attention to rate rather than event. Processes continue at slower pace, governed by reduced energy availability and increased separation. Stability emerges because change no longer occurs rapidly enough to disrupt existing structures. This behavior reinforces the importance of scale. Large outcomes do not require large forces applied suddenly. They result from small influences acting consistently over long durations. Space exemplifies this principle at every level. As the journey moves forward, emphasis remains on persistence under constraint. The universe does not move toward silence or stillness. It moves toward lower intensity states that still support motion, interaction, and structure. The same relationships between mass, energy, and time continue to apply. Nothing new is introduced. Nothing essential is removed. The environment remains governed, predictable, and continuous. This phase of space highlights endurance rather than creation. Structures that formed under favorable conditions remain. Processes slow, but do not stop. Space continues to operate as an environment where physical law sustains activity across immense spans of time. The exploration proceeds without urgency. There is no need to arrive at an ending point. Space continues as a system shaped by balance, persistence, and gradual adjustment, maintaining coherence long after the conditions that formed it have passed. As scale continues to dominate perception, the role of distance becomes more than separation. Distance shapes which interactions remain possible and which fade into insignificance. Forces weaken with distance, signals take longer to arrive, and influence spreads more thinly across expanding space. Gravity provides a clear example. Its influence extends without limit, yet its effect decreases steadily as distance increases. Within bound systems, gravity dominates motion completely. Beyond them, its influence becomes part of a broader balance, where expansion and other forces shape outcomes more strongly. This gradual weakening does not remove connection, but it alters its consequence. Radiation behaves similarly. Light continues to travel indefinitely, but its energy becomes diluted as it spreads. A signal emitted from a star may travel for billions of years, yet by the time it reaches distant regions, its effect is negligible. Information persists, even when influence does not. These properties redefine interaction at large scale. Early in the universe, proximity allowed frequent exchange. Later, increasing distance limits direct interaction while preserving shared history. Space transitions from a network of frequent contact to a system defined by inherited structure. Within this framework, isolation does not imply disorder. Bound systems retain coherence because their internal dynamics are sufficient to sustain stability. Planets do not require external input to continue orbiting. Stars do not require new material to continue emitting light. These systems persist through conservation rather than reinforcement. Distance, therefore, becomes a filter rather than a barrier. It allows local complexity to continue while limiting large-scale change. This filtering effect stabilizes the universe over long timescales, preventing rapid or widespread disruption. Time reinforces this pattern. As distance increases, the pace of change slows further. Interactions become rarer. Energy gradients flatten. What remains active does so because it is internally sustained rather than externally driven. Understanding space through this lens removes the expectation of finality. There is no point at which distance eliminates motion entirely. Instead, influence fades gradually, while structure remains. Space evolves by allowing systems to persist independently within widening separation. This behavior is not accidental. It arises from the way physical laws scale with distance and time. Conservation principles ensure continuity. Expansion alters context without altering rule. As this journey continues, distance becomes a defining feature of later space, not because it ends interaction, but because it reshapes how interaction matters. Local systems continue unchanged, while large-scale relationships loosen gradually. The universe remains coherent under these conditions. Motion persists, structure remains, influence adjusts rather than disappears. Space continues to operate as an environment shaped by scale, governed by consistent law, and sustained through balance rather than intervention. As distance reshapes interaction, attention turns to how space maintains coherence without central coordination. No region directs the behavior of another. Instead, order emerges from local interactions governed by shared constraints. This decentralized organization allows the universe to function without hierarchy or control. Local conditions determine outcome. Where matter is dense, gravity dominates and structure forms. Where density is low, expansion and dispersion prevail. These outcomes arise independently in different regions, yet they remain consistent because the same physical laws apply everywhere. Space does not require synchronization to remain ordered. This independence allows regions to evolve at different rates. Some galaxies continue forming stars actively. Others have entered long periods of stability. Some clusters experience frequent interaction. Others remain quiet. These differences do not disrupt overall coherence. They reflect variation within constraint. Time smooths these variations further. Processes that proceed quickly in one region may take far longer elsewhere. Over long intervals, averages emerge. Large-scale behavior becomes predictable, even as local detail varies. Space exhibits regularity through aggregation rather than uniformity. Energy flow reinforces this pattern. Local sources dominate local environments. Distant sources contribute minimally. This localization limits how far disturbance can propagate. Violent events affect nearby regions strongly, while leaving distant regions unchanged. This containment supports long-term stability. Fields continue to provide subtle linkage without enforcing uniform behavior. Gravitational fields overlap. Radiation passes through all regions. Magnetic fields extend across space. These influences connect regions without equalizing them, allowing coherence without homogeneity. This structure explains why the universe remains stable despite vast scale. There is no requirement for global equilibrium. Local balance is sufficient. As long as systems maintain internal stability, large-scale order persists naturally. As the journey continues, this principle becomes central. Space operates through countless independent processes that align through shared law. Order emerges without coordination. Persistence arises without reinforcement. This view removes the need for narrative endpoints. The universe does not move toward completion. It continues through distributed activity that adjusts gradually under constraint. Space remains open, governed, and self-consistent. Motion, energy, and time interact locally while contributing to global behavior. This decentralized coherence defines how the universe persists across expanding distance and deep time, maintaining structure without central control. As this understanding settles, space can be described through continuity rather than progression. There is no sequence of stages that must be completed. Instead, the same processes repeat under changing conditions, producing different outcomes depending on scale, density, and available energy. Motion remains fundamental. Objects continue to follow paths shaped by gravity and momentum. These paths are not directed toward outcomes. They persist because nothing interrupts them. Orbits continue until energy is lost. Expansion continues because no opposing influence halts it. Stability emerges where opposing forces balance naturally. Energy continues to move and transform. Radiation spreads outward. Matter converts mass into energy through long-lived processes. Heat flows from concentrated regions into larger volumes. These transformations do not require initiation. They occur because gradients exist and persist. Matter responds accordingly. Where energy can be lost efficiently, matter condenses. Where energy remains trapped, matter disperses. These responses shape structure continuously, without requiring thresholds to be crossed suddenly. Change occurs through adjustment rather than transition. At this stage of space, the emphasis is on duration. Systems that have formed persist because their internal timescales are long. A star may remain stable for billions of years. A planetary orbit may persist even longer. These durations far exceed the timescales over which large-scale conditions shift. Because of this, space contains many overlapping timescales simultaneously. Fast processes occur within slow frameworks. Local variation exists within global stability. This layering allows the universe to change without losing coherence. Understanding space in this way removes the expectation of narrative direction. There is no acceleration toward novelty or decay. There is only the continuation of processes under evolving constraints. Outcomes emerge because conditions allow them, not because they are required. As distance increases, influence weakens. As energy spreads, activity slows. As time extends, persistence dominates. These trends do not imply decline. They describe redistribution shaped by physical law. Space therefore remains active in a quiet way. It does not demand attention through dramatic change. It continues because nothing forces it to stop. The same relationships between mass, energy, motion, and time remain in effect everywhere. As the journey continues forward, this steadiness becomes the defining feature. Space operates through consistency, applied across vast scales. Change unfolds gradually, constrained and predictable in aggregate, even as local detail remains varied. The system remains coherent, not because it is static, but because its rules do not change. Motion continues, energy transforms, structure persists. Space remains an environment sustained by balance, unfolding steadily without resolution. As the universe continues under these conditions, the distinction between presence and absence becomes less important than the distinction between influence and effect. Space does not require dense matter everywhere to remain active. Influence travels farther than material contact, shaping behavior even where particles are scarce. Gravitational influence extends indefinitely, but its effects diminish with distance. Radiation carries information forward even when its energy becomes too low to cause change. Fields remain present even when their influence becomes subtle. These extended influences ensure continuity without requiring interaction. This allows space to remain structured without uniform activity. Regions of high density continue to evolve internally. Regions of low density change slowly. Both exist within the same system, governed by the same constraints, contributing to overall coherence. Time integrates these differences without smoothing them completely. Variation persists, but it remains bounded. No region evolves so quickly that it disrupts the stability of the whole. No region becomes so isolated that it falls outside physical law. Understanding this balance explains why space does not fragment into disconnected parts. Even as expansion increases separation, shared origin and governing principles maintain unity. Space remains one system operating across scale rather than a collection of isolated environments. As this exploration moves forward, emphasis remains on how little intervention is required for persistence. No mechanism needs to enforce order. The universe maintains coherence through constraint rather than direction. This behavior reflects the fundamental nature of physical law. Conservation ensures continuity. Scaling relationships ensure stability. Interaction limits prevent runaway change. Together, these principles allow space to persist across immense durations. The universe therefore does not age in the way living systems do. It does not wear out or decay toward disorder. It redistributes energy and matter in predictable ways, while maintaining structure where conditions allow. Change remains gradual and bounded. As you continue through space, this steadiness becomes increasingly apparent. What once seemed dynamic reveals itself as persistent. What once seemed empty reveals itself as governed. Space remains active not through constant novelty, but through continuous operation under stable rules. The journey continues without approaching an end. Space remains an environment where relationships persist, processes repeat, and structure endures across time that extends far beyond observation. As the view widens one last time, Space can be understood through what continues rather than what concludes. Motion remains present everywhere. Energy continues to transform and spread. Matter stays organized where gravity allows and diffuse where it does not. These behaviors do not depend on attention or measurement. They persist because the conditions that support them remain in place. Across immense distances, the same relationships apply. Light travels outward, fields extend quietly, orbits remain stable. Expansion continues at large scale, while local systems retain coherence. These simultaneous behaviors do not conflict. They define how space accommodates both separation and stability at once. Time integrates all of this without interruption. Earlier distributions shape later outcomes. Present conditions carry the imprint of long-past interaction. Future states unfold from what already exists, guided by the same limits that have always applied. Space does not require renewal to continue. It carries forward through consistency. What appears distant or abstract resolves into pattern through scale. Large outcomes arise from small influences applied steadily. Change slows without stopping. Structure endures without reinforcement. Space remains active because nothing within it violates the constraints that allow persistence. The environment you have been moving through does not pause here. Expansion proceeds. Radiation travels on. Bound systems continue there. As the view widens one last time, space can be understood through what continues rather than what concludes. Motion remains present everywhere. Energy continues to transform and spread. Matter stays organized where gravity allows and diffuse where it does not. These behaviors do not depend on attention or measurement. They persist because the conditions that support them remain in place. Across immense distances, the same relationships apply. Light travels outward. Fields extend quietly. Orbits remain stable. Expansion continues at large scale, while local systems retain coherence. These simultaneous behaviors do not conflict. They define how space accommodates both separation and stability at once. Time integrates all of this without interruption. Earlier distributions shape later outcomes. Present conditions carry the imprint of long-past interaction. Future states unfold from what already exists, guided by the same limits that have always applied. Space does not require renewal to continue. It carries forward through consistency. Thank you for listening to the Sleepy Mind channel. I hope you have enjoyed spending time moving through space.